So in this video, what I want to look at is integrals of powers of the secant function. And when I say powers, I'm talking about integer powers. And in particular, we're going to look at the secant function cubed, the integral of this, and also the integral of the secant raised to the power 4. And to calculate these integrals, we're going to need some standard relations. One of them is the derivative of the secant function, which, using the chain rule and writing secant as 1 divided by the cosine, we can find easily to be the secant times the tangent. And another is the standard result that the derivative of tangent is the secant function squared. And as well as this, we're also going to require the result that sec squared theta can be written as 1 plus tan squared theta. And this result is exactly the same as saying that 1 is sine squared plus cos squared and then dividing both sides by the cosine squared. So this is a very useful algebraic result for simplifying integrals that involve powers of secant or indeed powers of the tangent. So these are the basic results that we're going to need, and we're now going to look at how to calculate these integrals in turn. To do that, I'm going to move on to a fresh slide. So the first integral that we want to look at is the integral of the cube of the secant function. When we look at this, we don't initially see exactly how we can do it. We don't see any simple result for using a substitution or anything, but we do know something about the secant function squared. And that gives us a hint that it might be a good idea to write our integral as the integral of sec of theta times sec squared of theta with respect to theta. And this is a very useful trick when you're faced with integrals involving higher powers of the secant function, to single out a factor of sec squared because we know that this is obtained as the derivative of the tangent function. And also, if necessary, we can rewrite this in terms of the tangent squared. So let's look at this and think now that we have something here which we could differentiate and something here whose integral is fairly easy to calculate. The integral of this is tangent. Note that we don't want to look at it the other way around. We don't want to integrate this because the integral of this is the log of the modulus of the secant plus the tangent. And that's something very complicated. So going down that route is very unlikely to help us. So what I'm saying is that we're going to now consider using integration by parts. And the integration by parts formula is that the integral of u v prime with respect to theta is uv minus a different integral, the integral of u prime times v with respect to the same variable, in this case theta. And as we've indicated, this is easy to integrate, so let's use this as v prime, and that means we'll use this as u. So we're integrating this factor and we're differentiating this factor. And the word late that we often use to think about which factor to integrate, which factor to differentiate, is no help here because both of these factors are trigonometric. So what we're going to do now is say that u is sec theta, and that means that u prime, using the standard result that we should really know off by heart that was mentioned on the previous slide, u prime is sec theta multiplied by tan theta. V prime is the other factor in our initial integrand here, so it's sec squared theta, and the integral of that v is the tangent of theta. So the integration by parts formula, written here, tells us that we can rewrite this integral here, which I'm calling I, as u times v, so that is sec theta multiplied by tan theta, minus the integral of u prime, which is sec theta tan theta, multiplied by v, but v is just tan theta, and so instead of writing another factor of tan theta here, I'm just going to say that that means tan theta times tan theta, so we have tan squared theta integrated with respect to theta. Now when we look at this, we think this doesn't really seem to be working. This perhaps looks much more complicated than anything we had before, but it's at this stage that we remember the key result that we had on the previous slide, that sec squared can be written as 1 plus tan squared theta. Or in other words, we can write that tan squared theta is sec squared theta minus 1. And now we can take this result here, substitute it into here. So therefore our initial integral is sec theta tan theta minus the integral of sec theta times sec squared theta minus 1 is going to be broken up into two terms. Sec theta times sec squared theta is sec cubed of theta minus sec theta, all integrated with respect to theta. I'll put brackets around all of this. So what we have here is an integral of a difference of two terms, or in other words, we have the integral of this minus the integral of this. Now the integral of sec cubed theta is our initial integral. It's what we have been calling I. So this integral is going to be I. So what we're going to do now is to recognize that here we have minus I, so we're going to add I to both sides, in other words take this over to here, and we're going to get I plus I, that's a minus sign, so I plus I, so 2I. So this tells us, gathering the initial integral structures together, that 2I is sec theta tan theta minus, and then we have another minus sign here, minus minus, so that becomes plus the integral of sec theta with respect to theta. And this is a standard integral whose result we know. It is the log of the modulus of sec theta plus tan theta. So we have this, we know what this is, and here there's a factor of 2, so we're going to divide both sides by 2. So I, which is the integral of sec cubed theta with respect to theta, is 1/2 sec theta tan theta plus 1/2 the log of the modulus of sec theta plus tan theta, close the modulus, plus an integration constant which we don't know anything about at the moment. So this is our result for the integral, and the key factors that we've used in obtaining the integral were, first of all, we looked at the integrand and we recognized that we could factor out here a factor of sec squared theta, and then we have a product of two structures, one of which is easy to integrate, and integration by parts is a technique that naturally offers itself. Using integration by parts, we obtained this, and this new integral here looked for a moment complicated, but once we realized that we can rewrite tan squared theta as sec squared theta minus 1, then we were able to obtain our initial integral here, and we could bring that over to here to have twice the initial integral, and the integral that we were left with here, the integral of sec theta, is a standard result. So in this way we were able to put everything together and to obtain the integral of sec cubed theta. And I would encourage you now to check that this integral is correct by differentiating this side with respect to theta and seeing that you indeed obtain sec cubed theta. And that is going to be very good algebra practice. And with that, I'll pause this example, or stop this example, and move on to the next slide where we're going to look at the integral of sec to the power 4 of theta. So in this slide I'm going to calculate the integral of sec to the power 4 of theta. And to do it we're going to use techniques very similar to those on the previous slide. So you might like to try it first of all and then just to fast forward through my answer. And if you want to do that, I would encourage you to write it down and try it on a piece of paper, so you might want to pause the video now. Okay, welcome back. So again, what we do now is we think we don't know how to integrate sec to the power 4 of theta immediately, but we do know how to integrate sec squared. So what we're going to do is to write this as a product of sec squared of theta times sec squared of theta integrated with respect to theta. And we're going to use integration by parts, so we're going to integrate one of these two identical factors and the other factor we are going to differentiate. So it doesn't matter which one is which because they're absolutely identical. Let's call this u and let's call this v prime, and the derivative of u prime is going to be 2 sec theta multiplied by the derivative of sec theta. So all I'm doing here is using the chain rule, d by d theta of sec theta. So therefore u prime is 2 sec theta, and the derivative of sec theta is sec theta tan theta. So the extra sec theta factor, I'm not going to write it here, I'm going to write this instead as a square. So it's 2 sec squared theta tan theta. And similarly, v is the integral of sec squared theta, and that's very easy. The integral of sec squared theta is the tangent of theta. It's a standard result we should all know. So we're now going to use the integration by parts formula. So we use that the integral of u v prime is u v minus the integral of u prime v. So therefore we see that our integral I is going to be uv, well u is sec squared theta, v is tan theta, so we can just write sec squared theta tan theta minus the integral, and now it is u prime times v. U prime is 2 sec squared theta tan theta, so I'll take the 2 outside of the integral, and then we have sec squared theta tan theta. This is u prime. V is tan theta, so we're going to multiply here by another tan theta, and tan theta times tan theta is tan squared theta with now respect to theta. So we look at our new integral here, and again we think we can rewrite tan squared theta as tan squared theta is sec squared theta minus 1. So we're going to have, therefore, that our integral, is sec squared theta tan theta minus 2, and then I'm going to open brackets because the minus 2 is going to multiply both of the terms here, sec squared theta times sec squared theta minus sec squared theta times 1. So we're going to have the integral of sec to the fourth of theta, and that's just our initial integral I, minus the integral of sec squared theta with respect to theta. I'll close the brackets that I've opened here. So these two terms correspond to the integral of sec squared theta times sec squared theta, our initial integral, minus this integral of sec squared theta times 1. So now we have minus 2 times the original integral, so I can bring it over to here. I know that I'm adding 2 times the original integral to both sides, so we're going to get that 3 times the original integral is sec squared theta tan theta. Then we have minus 2 times minus is going to give us overall plus 2. And now we have the integral of sec squared theta, and the integral of sec squared theta is just the tangent of theta. And then let's add to this an integration constant, which I won't be too explicit about. So therefore our integral is 1/3 sec squared theta tan theta plus 2/3 tan theta plus an integration constant. And that is our result for the integral. So again, the key results that we used to obtain it were to pull out of here a factor of sec squared theta that we could integrate. We used integration by parts, and doing that we again had to use this relation that tan squared theta can be written as sec squared theta minus 1, and we recognised our initial integral and brought all the terms containing the initial integral over to the left-hand side. So this is our result for the integral, but we can also ask ourselves whether it is possible to simplify this, and to do that I'll make a little bit of room. So to simplify it, what I want to do is to rewrite it completely in terms of the tangent function. And the reason that I can do that is because here I have sec squared of theta, and we know that we can write sec squared of theta as 1 plus tan squared theta. We can't rewrite this in terms purely of the secant function, because here we have the tangent function to the power 1, here again we have the tangent function to the power 1, and we don't know up to signs, or we don't know about the sign of writing that in terms of the secant. This can be positive or negative, but this is sec squared, and sec squared can be written as 1 plus tan squared. So doing that, we write this as 1 plus tan squared, so we are going to get 1 times tan theta with a third, which is going to go with that, and 1/3 plus 2/3 is 1. So we're going to get that our integral, the integral of sec to the fourth of theta with respect to theta, is going to be the tangent of theta. That's the 1/3 plus the 2/3. And then we have 1/3 times tan squared times tan, so that's tan cubed, so it's plus 1/3 tan cubed of theta plus an integration constant. And that is our result for the integral. And on the next slide, I'm just going to make a few comments about higher powers. But I would first encourage you to check that this is correct by differentiating the right-hand side and showing that you obtain sec to the fourth of theta. And that's not going to be too complicated to do. So to calculate integrals of higher powers of the secant, so n greater than 4, the efficient way to calculate them is to use a reduction formula. So defining the integral in to be the integral of the secant to the power n, and again we're thinking of n as being a natural number, a positive integer, then the reduction formula that one can obtain is that in is equal to 1 over n minus 1 times the secant to the power of n minus 2 of theta times the tangent of theta plus n minus 2 over n minus 1 times the integral with the label n minus 2. So this notation here means exactly the same integral, but with n here replaced by n minus 2. So this is an example of a reduction formula, and what I would encourage you to do now is to use the previous examples as a way of checking this. So an exercise is obtain the result above. And a final comment to conclude the video is that we notice that what's happening here is that we're always going from in to the integral in minus 2. So we are dropping the power of the secant by 2. And when we use a reduction formula, we're always trying to use it to obtain an integral which is fairly easy. So let's imagine that n was 5. You would use this reduction formula with n equal to 5, and that would give you the integral I3. You would then reuse the formula to go from I3 to I1. I1 is the integral of sec to the power 1. The integral of sec is a standard integral, so we can do it. So for odd powers, such as I5 or I7, we always reduce down to I1, the integral of sec to the power 1, standard integral. If we're looking at higher even powers, so for example if we were looking at I6, imagine n was 6, that would reduce down to I4. We would then reuse the formula to go from I4 to I2, and I2 is the integral of sec squared, and that is just tangent. That is again a standard integral. So we should be careful when we use this. We should always think, what are we trying to get down to? What is the final integral that we are able to calculate? And with that exercise for you to do, I will conclude this video.